Right, in this lesson, we are going to work on a couple things. So we've got the goals up at the top. You're going to be able to tell me the domain and range of continuous functions based on their graphs. You're going to be able to identify key features of the graphs, which would include x and y intercepts, extreme values, and then of course domain and range are key features as well. And then you're going to be able to describe the reasonable domain and range of a function based on context. So this meaning like a real life situation and the restrictions that it would bring along with it. So when we are looking at these, we have two different graphs. This is a graph describing the glitch roller coaster, and then this graph is one that describes the thunderball roller coaster. So the first question we want to answer is, how are the two graphs similar and how are they different? So I think the most obvious thing is a difference, and that would be difference, glitch is just points, whereas the thunderball has curves connecting the points. One way that they are similar is that if you actually look at the locations of the dots, they're all the same. So same location, same values. So exact points that we plotted are the same. So both the x and the y coordinates were the same. So what we want to talk about is the difference in these key features. So the domain of the glitch, because these are just individual points, remember that domain is the input or the x values. Remember that we had that saying Dix Roy. So domain, input, x values. So the domain here is the x value of 0, because that's the x value here. And then right here, it's 250. This one, let's see what we're counting by. 550, 600, 650. Yeah, we're counting by 50s. So this x value would be 550. This one right here, it's one past the 750, which makes it 800. And then finally the 1250. So those are my individual x values. That gives me my domain. Likewise, the range here are going to be the individual y values. So the first one we have 10, followed by, looks like 110. This one over here looks like 30. This one, 90. And that's 10 again, so we don't need to list it twice. I can actually go ahead and close the brace there. When we are looking at the thunderball, however, the domain is, because these curves that connect, it means that everything that's between these values is included. That if I wanted to, I could go through and make a little exact point on every single x value that I wanted, as long as it's between the endpoints. So my x values start at 10 and they end at 1250. So the way that we write this is using our inequality sandwiches. So we learned about those when we were talking last week about the compound inequalities. And so an inequality sandwich is where we put our variable, in this case x, And that's kind of the meat of the sandwich. And the buns in this case are the lower and upper limits. So the lower limit on x is 0 because that's the x value here at this point. The y value is 10, but the x value is 0. And there is an exact point there. There's a closed circle, so we're going to include it. So x can start at 0, and it can go all the way up and also includes, because it's a closed circle, the 1250. So that means that my domain, what this is saying, is that x can be anything between those values. Remember that when we write an inequality sandwich, both of the symbols should be a less than, always. Sometimes they get the equals if it's a closed circle. If they're open circles, then they would not. We do the exact same thing on the range, but remember from Dix-Roy that the range are the output or the y values. So when I'm looking for domain on a function that has curves or lines, I'm looking really for the walls. I'm looking on the left and then I'm looking on the right because that's which way the x-axis goes, from left to right. When I am looking for the range, I'm looking for the floor and the ceiling. So I'm going to look for the very lowest point. So looking down, the lowest y I see here is 10. I look across to see if there's anything below that. Nope, 10 is the lowest y value that I see. So that's going to be the lower limit or the left side bun on my inequality sandwich. Then, after I found the floor, then I look up to find the ceiling. So I've got lots of different, points here. I'm looking for the very tallest ceiling that exists, and that would be right here. And that y value there is 110. And it is a closed circle, so we will put the equals on that. So what I say when we have graphs that have connectedness, they have a line or curves between the exact points, is that for domain, we're looking for walls. For range, we're looking, and this is left to right. So if you look at it in the sandwich, leftmost goes on the left side, rightmost goes on the right side. For the range, we're looking for the ceiling and the floor. So that means we're looking down and then we're looking up. So down to get the lowest value, up to get the highest value. All right, next key feature we're going to look at is maximum. And so there is a difference in something that we call a relative maximum and an absolute maximum. And we're going to define those momentarily. If it just says maximum or minimum, then assume that it's absolute. So maximum that we're looking for here is the highest y value. So I look on my glitch, the highest y value would be in the range, and that'd be 110. I look at the thunderball, the highest y value, which I have listed on my range, also 110. Excuse me, glitch minimum, lowest y value. So again, we're only looking at the y's. Min and max are y values. So I look, the lowest y value that I see on the glitch is 10. Over here, look at my range. Yep, it's 10 there as well. The glitch y-intercept. Remember that a y-intercept is the place where it crosses the y-axis. So if I look at my y-axis here, the only point on the y-axis is 10. When we write intercepts, they need to be written as ordered pairs. So write yourself a note here, ordered pair, always. Don't just write 10. You need to write 0, 10. When I look at the thunderball, only place on the y-axis is in the same place. Now, interpreting it in context means, what does that mean? Well, this y-intercept, when I interpret it in context, I just put basically the labels. So I would say that when the distance is 0, or at its starting point when distance is 0, so when distance along track equals 0, and then say what this is, height above the ground is 10 feet. I should probably say equals 0 feet. Over here, I'm just going to write same because all the labels are the same. Distance along the track in feet, height above the ground in feet. So this y-intercept means the same thing in both cases. X-intercept would be the place where it crosses the x-axis. So I look on the x-axis and I don't see anything. So there is no x-intercept. Same thing on the thunderball, nothing to report. So, last thing is going to involve some more definitions. Determine if the graphs are continuous or discrete. So, here's where we have some definitions. Continuous functions are connected. You can draw the entire graph without picking up your pencil from the paper. These typically come from measurements like distance or time, something that is a continuous variable. Discrete functions are individual points that are not connected. These typically come from counting values where we're only using maybe whole numbers or only using rational numbers. But discrete functions are where we have just an individual collection of points. Continuous functions, we're going to have connection, either with curves or lines, or some curves and some lines, but there is a connectedness. You could start at the very beginning with your pencil, trace the whole thing without ever picking it up. So I want you to go ahead and pause, and I want you to determine what type of graph each of these is. So I'm going to ask you about both the glitch roller coaster and the thunderball. Tell whether each of those is continuous or discrete. So for the glitch, when I look at its graph, is just a collection of individual points. So that fits the definition for discrete. So if you said discrete, you are correct. The thunderball. When I look at it, I could start with my pencil here and draw the entirety of the graph without ever picking up my pencil. So that means that it is continuous. So hopefully that helps those definitions to make a little bit more sense. Part J, use the vertical line test to determine if the graphs are functions. So we did the vertical line test in previous lessons. So if I draw a vertical line here, there are never any two dots that it's going to touch. So the glitch is a function. Now I'm going to look for the thunderball, and I can draw a whole bunch of vertical lines. None of those are touching the graph more than once. So that means that the thunderball is also a function. All right, next, what are extreme values? And in math, we will call these extrema. Extrema is just the plural version for basically an extreme value. So the types of extrema that you want to know are absolute maximum, absolute minimum, relative maximum, and relative minimum. So the absolute maximum is the biggest output value. So it is the y coordinate, and that is so key, y coordinate only for maximums of the highest point. So we find the point first, then we read its height from the axis. So here on this particular graph, here's the highest point. I go over, that's 110. So that is my absolute maximum. The absolute minimum is the smallest output. So again, still y coordinate of the lowest point on the graph. In this case, there are kind of two lowest points, it looks like, but either way, that y value is 10, so that is the absolute minimum. And remember, as I told you earlier, if it doesn't say whether it's supposed to be an absolute or a relative, then it's understood to be absolute. So if it just says maximum or minimum, it means absolute maximum or minimum. In contrast, relative max and relative min are what we would say are the tops of hills and the bottoms of valleys. So a graph can have multiple relative maximums or multiple relative minimums. The key is that they cannot occur at the end points of the graph. So when I'm looking for relative max, in this case, top of a hill is going to be a relative max. So my absolute max is at the top of a hill, so that one would count. So 110 would be one. And this one is also a top of a hill. And if I go over there, looks like that value is 90. So I have a relative maximum there. Sometimes they'll ask you for the coordinates of the relative max or min. If it says coordinates, then we would write ordered pairs. When I go to do the relative minimum, I cannot include the absolute minimum in this case because those are both endpoints of the graph. So those can't be included, which means the only relative minimum is the bottom of this valley right here, and the y value there looks like it's about 30. So no endpoints. You cannot include the endpoints of the graph. All right, so now it is time to apply what you've learned in the example I went through in a new example. So this says Cougar Mountain is another roller coaster that immediately starts climbing the track in a linear fashion as shown in the graph. So this time we don't have curves connecting, we have a line. So some of these key features I'm going to do, and some of them I'm going to ask you to fill in. So domain, again, remember, Dix, Roy, domain, input, x values. So this, because it's connected, that means that I'm going to write an inequality sandwich. So I start at where x is 0. It is a closed circle. And I end where x is 200. So my domain should go from 0 to 200. Next, for the range of the function. So what I want you to do is tell me what the lowest and highest points should be. In other words, I want you to fill in what the minimum and the maximum are on this inequality sandwich, because range is going to look like this. So first, go ahead and tell me what should go over here, and then tell me what should go over here. All right, so range output y values. Remember what I said way back up here. When I'm doing the range, I'm looking for ceiling and floor, looking down and then looking up. So looking down for the floor, lowest y value I have here is 0. So that's what should go there. Then I look up for the ceiling. It's right here. So it looks like I'm counting by 25s. So this would be 175. And they're closed circles, so they do get the equals. All right, next, y-intercept crosses the y-axis there at 0, 0. What does it mean in context? That when distance along track is 0 feet, the height above ground is 0 feet. All right, what is the absolute maximum? So the very highest point. Well, the very highest point that we see here is 175, but it is an end point, which means that I cannot include it. So that means, oh, never mind. I don't know what I'm thinking. The endpoints can't be included for relative maximum and minimum, so we're okay here. So absolute maximum highest point here is 175. Absolute minimum, very lowest point here is 0. Remember, these are all y coordinates. And so then G, does the function have any relative maximum or minimum values? This would be a no, because there are no tops of a hill or bottom of a valley, and I'm not allowed to include the endpoints there. All right, last topic is reasonable domain and range, which takes into account real-world situations. So if a function describes the number of people in your class, we wouldn't write an inequality sandwich. We wouldn't say, x between 0 and, 25, because x can't be anything between those numbers. It could only be whole numbers. However, if we're talking about shoe sizes, we might include whole numbers. Actually, we would include natural numbers plus like half sizes, but you wouldn't have any other decimal points. So the real world context really kind of tells you what your domain should be. So here we're going to write a function and give reasonable domain and range for the function based on context. So whenever it says reasonable, it means you have to consider real life restrictions. So what do the variables stand for? And so what restrictions might I have because of it? So part A, a banquet hall charges $22 per person plus a $100 setup fee for a party with dinner. Write a function for the cost of X people attending the party. So we would say, so writing the function, and it does say function, so that means function notation. I'm going to call my function C of X because it says X people attending the party, so X needs to be my main variable. C of X means cost for X people. So it says $22 per person. So 22 times X plus a $100 setup fee. Now, that $100 setup fee does not say per person, so that's just a straight value. So, reasonable domain, when I'm looking at this, we are talking about people. So, the least number of people that you could have attending would be one person. You can't have 0 people because who's going to pay for something that they're not even going to, right? So 1 would be first, then 2, 3, 4, so on and so forth. These 3 dots are called ellipses. It just means continuing in the same pattern. And so what we ended up here with is that our domain is whole numbers. So there are going to be times where they're going to actually use those descriptions of types of numbers. Instead of writing it out like this, they might say domain whole numbers. A reasonable range. Well, your range needs to consider your domain. So if x is 1, that would give us 22 plus 100. So that'd give us 122. Then if I had 2 people, that'd be 44 plus 100, which means that I'm going to end up with values that are all bigger than or equal to 122. So I could say, and I shouldn't say y because I used the variable c, right? So c is going to be greater than or equal to 122. If you want to start listing them all out, I suppose that you could, but most of the time we're going to write them like this. All right, last one. At an ultimate tournament, teams must have at least 7 players and no more than 29 players. An ultimate tournament costs an entry fee of $250 plus $25 per player. Write a function to determine the cost of a team based on the number of players P attending a tournament. So in this case, I know I'm going to use y this time. Y equals, so cost equals, since I already used C, it's $25 per player, so 25 times P, and then plus that entry fee of $250. Now, in this case, you might think, all right, I'm going to start exactly the same way that I started here. And I could have 1 person, 2 people, so on and so forth. But that's not actually true because we have additional information given to us by the situation. It says teams have to have at least 7 and no more than 29. So the way that you could write this is you could either write, you could say domain is whole numbers between 7 and 29, or you could write them out, 7, 8, dot, 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 28, 29, all the way up to the other end. A reasonable range. So range, I know that the least amount of money that might be spent is if there are only 7 players. So 25 times 7 plus 250 is going to be the lowest number. I know that the highest amount, because it can't just keep going and going and going and going. Here we aren't told anything about an upper limit for the number of people attending the party, but here we are. We're told no more than 29 players. So this is going to be our high value. So we're going to end up with our y being between, so 25 times 7 plus 250. So 25 times 4 is 100, so this is 175 plus 250. So 175 plus 250 is 425, so that's my low value. Then for my upper value, definitely going to need the calculator for that one. 25 times 29 gives me 725. And then I have the 250 to add, which gives me 975. So y values could be in here. It would be okay here with me if you wrote 7 to 29 with x, even though technically it's only the whole numbers. In most contexts, we allow this type of answer. All right. That is it for that. Please reach out if you have questions.